So today we're going to look at 7.3, which is on solving trig equations using a graphical approach. We're going to do this exact same thing again in section 7.6, except the title is going to be solving trig equations algebraically instead of graphically. So graphically, we can solve anything. You pretty much put something in y1, you put something in y2, you see where they cross. It's pretty straightforward. Okay, a few details that we need to mention. Algebraically can be harder. And there are only certain equations we can solve algebraically if they're trig. They got to work out nice somehow. And by nice, I mean it has to be something that we could factor. It's got to be something we could use quadratic formula on. Something has to happen that works for us. Okay? But graphically, we can do anything. The only downside to graphically is all your answers are decimals. Because when you calculate an intersect, it is never exact. If they ask for exact answers, which in 7.6 they will, you have to do it algebraically. You cannot use the calculator like we're going to do today. All right, so let's see what's in the section. So this is just a review of how you find solutions when you're dealing with a periodic equation, okay, or a trig equation. The idea is find all solutions in one cycle. That means you need to know how to figure out the cycle length. What's the formula to find the cycle of sine, cosine, secant, or cosecant? It's the t equals something. Mm-hmm.
Something over b.
Something over b.
And like the slope over b, or the thing that's in cosecant, secant.
Quite, yeah. Okay. 2 pi over b. That's how you find the slope of sine, cosine, secant, cosecant. It's not slope, period. How about the formula for the period of tangent and cotangent? Yeah. Pi over b. And remember, b is where in the formula? Where would you find the b? Yeah. Inside the parentheses in front of the x. Okay, so to find all the solutions, first, find all the solutions in one period. That means graph it on the screen, set your window to one cycle. Okay. Next, we find all the solutions by taking into account the period. So you basically do plus the period times an integer, any integer. Usually we use n. Might see different letters, but plus the period times n. Okay, so that's review. Okay, that's what we've been doing for quite a while. Any questions on that? Yes.
You said 2 pi over b was for which trigonometric functions?
Everything except tangent and cotangent.
Got it.
So when we've graphed trig functions before, we've done like sine x, we've done 3 sine 2x, or we've done like tangent x plus pi. We've done one function per graph. Well, we're going to look at graphing something like this eventually. Okay. It has more than one function. So we're graphing cosines. First of all, we're graphing a sine and a cosine. And we're graphing something to a power. So we're going to have to come up with a formula to see how does cosine squared fit in. It is going to either be 2 pi over b or 1 pi over b. Those are the two formulas you always use. But we're going to have to extend those formulas a little bit to cover the case when you have an even exponent or an odd exponent. So we can use those formulas for even more than you know right now. And I'll show you how that works. All right, so let's look at this one, just kind of a review. Sine of x equals 0.8. Right away, when you look at that, you're solving for x. X is X represents what?
The argument?
The argument, and the argument is it's an angle. You're solving for an angle. When you're solving for an angle, you should start thinking of this right away. Okay, you're going to need that to solve this. What do we do on each side to get the x by itself? Yep.
Take the inverse sign.
Take the inverse sign. And if you type in exactly what you see there, you will get one answer. So let's do the inverse sine of 0.8. Okay, I'll do it in degrees. So we get 53.13. Still a few more things we got to do. First of all, we need to take into account all solutions. So can somebody describe this solution for me, continuing forever? Yeah.
You've got to add 360 degrees n for the number of times that it repeats.
Yep, because the period is 360.
There's also going to be a second solution.
Yes, there is.
Which we need to subtract the number that we got from the calculator by 180.
Right. So each second solution needs to be in the second quadrant, because we're looking for where sine is positive. So it's 180 minus 53.13.
How do we know if it's 180 or 360 again?
So 126.87. So each quadrant has its own formula. So the question is more, how do you know which quadrant you need to be in? And then the formula is automatic. How do I know I need to be in quadrant 2? And the formula in quadrant 2 is automatically 180 minus. But why quadrant 2? Yeah.
Because sine is specified to quadrant 2 and quadrant 1.
Because what happens with sine in quadrant 2?
I just know if sine goes in quadrant 2.
Well, it depends. Sine isn't automatic. Well, I need to know more about what's happening to sine in quadrant 2. Yep. It's positive.
Because it's y?
What's that?
Is it because sine is like the y?
Yeah. Yeah.
So, like that with all the okay.
Yeah.
Then what does that mean for t?
Well, for t, when you're in tangent, that's quadrant 3. So in quadrant 3, tangent is the only positive value. Everything else is negative in quadrant 3. So we're looking for where sine is positive. That's quadrant 1 and 2. We already have an answer in quadrant 1. So now we need to do 180 minus. And don't forget, plus 360 n. Okay, so you can add 360 to each of those numbers, and that would give you the answer in the next cycle. If you subtract 360, you get the answer in the cycle before. And you can keep doing it forever. Any questions how we got those two answers, or how you do it in radians? Okay. So remember that when you set something equal to 0 and you solve it, that's called finding the roots, okay, or finding the zeros of the equation. So that's just a reminder, we did that a lot at the beginning of the year. If you see directions in a problem that say find the roots of the following equation, all that it means is set it equal to 0. Okay, so just a reminder about that. Okay, any question on that? Finding roots, finding zeros? Okay.
Actually, is that like the liner, the x-axis stuff?
When you're finding the roots, that is where it crosses the x-axis. Yep. All right, so I said that you have to find all the solutions in one cycle. So let's say that these represent all the solutions in one cycle. Since we're doing more complicated graphs, like with higher powers, multiple trig functions, we may get a lot of answers in one cycle. I think there's one problem we do that there's 6. It means it crosses the x-axis 6 times in one cycle. So you find each one of those solutions in one cycle. And remember, you can find them by doing second calc 0. Second calc 0 will help you find the roots. Doing second calc gives you the answers in one cycle. Then it's up to you to do that answer plus the period times n. And then the second answer plus the period times n. The third answer plus the period times n. All the way up to the last answer plus the period times n. Okay, so I'm just emphasizing you need to put plus the period times n on every answer. Remember, n is an integer. You cannot add a partial cycle to an answer. You can add a whole cycle, you can subtract a whole cycle. Nothing in between. Okay, I'm just kind of saying the same idea again another way. So what we need to talk a little bit about is how do you find the period? Well, we've got the formula pi over v and 2 pi over v. But what happens when we have a more complicated trig function? Okay, like cosine squared and sine. How do we find the period of that whole thing? Well, the first thing we have to do is find the period of each periodic term. Okay, so what's a periodic term? In that problem, cosine squared is periodic, sine is periodic, 1 is not. 1 is a constant term. So we have to find the period of each term that's periodic. Once you find the period of the first term, and then the period of the second term, you have to take the least common multiple of those. So let's say one of them had a period of 2 pi, and the other one had a period of 3 pi. That's not what this problem on the right is. Okay, but let's say you had a problem, and one had a period of 2 pi, and one had a period of 3 pi. What's the least common multiple of 2 pi and 3 pi?
Pi. 6 pi.
Yeah, the least common multiple can't be any smaller than these individual numbers. So the least common multiple there is 6 pi. Okay? So least common multiple, 6 pi. Most of the time, the least common multiple is going to end up being pi or 2 pi. That's usually what it comes out to. All right, so let's look at this one on the right. Let's start with sine. What's the period of sine t? Just regular sine, no transformations at all. Yep, 2 pi. Now, we don't know a lot about cosine squared. We've never graphed it. We don't even know what it looks like. But does this 2 have any effect on the period of what function comes after it? Yeah.
The way it's going to affect it is that it's going to be a vertical shift. It's going to be a vertical change, which is yeah.
So is the 2 going to have any effect on the function that comes after it? Any effect on the period?
Well, like, on the appearance or what we can put into it?
The period. Will the 2 affect the period?
Yes.
This 2.
Yes.
What kind of transformation is the 2? It's a vertical stretch. Period measures what kind of distance?
Oh, horizontal.
Horizontal. So does this 2 have any effect on the period? No.
No.
All it's going to do is take a graph that looks like this and make it look like this. It's not going to change anything left to right. So I don't really care about the 2 in the front. What I do care about is cosine squared. Okay, I want to graph that. just by itself, because I've never drawn it before, and I want to see if I can figure out what the period of cosine squared is.
Is it even possible to type on these calculators?
Yes. So remember, you can't type it the way that it's written. That's a notation that only you see on paper. The way you have to do it on the calculator is cosine x. And you do need the exponent outside parentheses. If you don't put it outside, you're going to be doing this. That is not what we're looking for. It's not the cosine of x squared. Order of operations, we want to take the cosine of x, get that answer, and then square the result. That's what this means. So this means what I have on the calculator right there. All right, let's set a window in radians. Let's go from 0 to 2 pi. Okay, let's just look at that window and see what happens. I'm also going to set this to be -2 to 2. So if you type that in through the window, let's graph it. And this is what cosine squared looks like. Okay, let's look at that. What did I set my window to when I did that? Yep. I did 0 to 2 pi. So right in the middle is 1 pi. How many cycles do you think you're looking at in that picture? Yeah?
Well, we're looking at 2 cycles right there.
You're looking at 2 cycles.
We have, it's pi, which is the period for this one.
Yep. So the period of this is going to be pi. There's 1 cycle in black. Here's another cycle in green. So cosine squared has a cycle length of pi. In fact, any trig function to an even power is going to end up using pi as its base cycle. So we're gonna break that down in a minute with a chart. When do you use pi over b? When do you use 2 pi over b? And we're gonna break it down by having an even or an odd exponent. If this was cosine to the 4th, the period would still be pi. It would look a little different, but you would still see exactly 2 cycles on the screen. I don't know if you can tell that it looks a little different than cosine squared, but it is. It starts to flatten out a little bit more. Yeah.
Cosine squared, is it always positive?
Yes. Same with cosine to the 4th, cosine to the 6th. It's always positive because you're raising something to an even power, which cancels the negative. The only way that it could come out negative is if you shifted it down. Then you can make it negative.
Yeah.
But if you don't do any transformations, that's what cosine to an even power looks like. The higher the power, the flatter this starts to get, and the steeper this curve in the middle starts to get. Yeah.
For the odd and even powers thing, it's not like the square root of I thing, where it's like, with the I thing where like I is the square root of like -1, so you have the odd power like 3 or something, it's going to be negative.
Yeah, we're gonna make a chart.
But like it's like that.
Kind of, yeah. And so you can see what happens if I raise it to the 10th power. The point is you're still getting 2 cycles. It's just that flat part's getting more exaggerated, and so is kind of the peak in the middle. All right, so we've got a cycle length of pi for cosine squared. We've got a cycle length of 2 pi for sine. What is the least common multiple of 1 pi and 2 pi? Yeah? 2 pi. So now we know what to put on the answer to represent all solutions. Plus 2 pi n. Now we're going to take the whole thing. Okay, so let's put in 2 cosine x squared plus sine x plus 1. And we know the cycle length is 2 pi. So I want to set a window that's 1 cycle. I already have it set up, 0 to 2 pi. Okay, I'm just going to expand that to go from -3 to 3. Make sure I typed everything in right. Hit graph. I should have gone a little bit higher. Let's go up. I'm going to change the y max to 4 because it's right on the edge of the screen. All right. So that's what the graph looks like. Okay, that is one cycle. So that means if you took this, put it here, and you trace it. Wait, no, that's not the graph. That's the graph. Well, it's I don't know. It's stuck on the other one. Well, if you took this and you traced it, and you put another copy next to it, that would be the next cycle. Okay, so that is one full cycle. The end of your cycle should always be at the same y value as the beginning. That's the only way they would match up. Think about like if you took this and like bent it around, made like a cylinder out of it. These two things should match up and connect. All right, so they're asking where it equals 0. How many times does it look like it crosses the x-axis? Yeah, it looks like once. You could zoom in a little bit. There's no question that it only crosses in that area, right there. Let's just see if it goes below and comes back up.
You could do minimum, second calc minimum.
Yeah, so we could calculate the minimum, and we know that if the minimum is a negative, then it did drop below. If it is not a negative and it comes out to exactly 0, then we know it never crossed the axis. Yep, that's a good point. So the y value is 0. That's as low as it goes, which means it never does cross the axis. So that is where it touches it then. The minimum is the point of contact. 4.71. Okay, so that's your answer. And how often does that answer repeat? Yep.
Once. Oh, every cycle.
Every cycle. So what would you put on the end of it?
Plus 2 pi.
Yep. And that's the answer to that problem. Yes.
For the irregular wave that has like the one they have in the graph that has like multiple like different kind of multiple different like things on it. Is that like another thing in math to like figure out the calculations for the different waves to make up one wave? Because when you opened up the graph, it wasn't like a clean up and down; it was like irregular. And so it's not like another big part of math is like figuring out what makes up the regular waves and everything.
Yeah, I guess you could look at a picture that's not a regular wave and try to reverse engineer it and figure out what equation to make that up. That could be pretty challenging to do. Kind of like mixing colors of paint together and kind of separate the colors back out. That could be kind of hard.
I just thought that was like a big part of.
Yeah, analyzing waves. Yeah, there's all kinds of stuff with waves. Yeah. All right, let's look at this one. Let's treat it like we did the last one. We were solving for 0 in the last one. How could I get this equal to 0? Yeah.
Can you just subtract tan x or take out tan x, put it on the other side?
We can subtract it. Yeah, we could subtract either one of them. and put them on the other side. So if you do,
Easier way?
well, which way do you want to do it? Do you want to subtract the tan x to that side, or do you want to bring the 3
I
cosine
think it
x?
makes sense to take out just the 10 x.
All right, we can bring the tan x to the other side. It's not easier or harder really anyway. And it's not going to change the roots. It might change the picture, depending on which one of these you make negative. I think it would. But it wouldn't change where it crosses the x-axis. All right, so let's graph 3 cosine x minus tan x. Actually, no, first I need a period. What's the period of cosine? Yeah, 2 pi. What's the period of tangent? Pi. What's the least common multiple? 2 pi. I think it's 2 pi for almost every problem we do today. It doesn't have to be, but it just happens to be. All right, so window needs to be 0 to 2 pi. So I'm going to set that. Tangent goes up and down forever, so we're going to have vertical asymptotes in this one. So as far as what I would do for y, I might do like -8 to 8. Just set that up. And then type in your graph. 3 cosine x minus tan x. And remember, you should expect vertical asymptotes. So there's one. And there looks like a second one. Okay. So that is what your graph looks like. And it does look like that it starts at the same height that it ends. So if you connected those, it would continue on. All right, how many times does it look like this crosses the x-axis? Yeah, twice. So let's do second calc 0. Okay, I'm going to do the one in the middle. If somebody else can do the one on the left, that would be helpful. So the second answer is 2.13, and that's going to repeat every 2 pi. And what about the first answer? It's about 1. Looks like it's about 1.01. And that one will repeat every 2 pi. Any question on that?
Best you finish writing it down. Just the x values.
Alright, let's try this one.
I have a question.
Yeah.
When it comes to like having multiple trig functions, do you still think about like the SATC chart?
We don't have to think of, that's more of an algebraic thing we would have to get into. When we get into doing it algebraically, we're going to think more about quadratic formula to solve it. This would not be one we could do with quadratic formula because it's cubed, but this last one doesn't look like quadratic formula, but it would be. That is quadratic formula. And the one before it is clearly quadratic formula. Yeah. This one would not be. I don't know if this is one we could do algebraically, but the first two we could have. All right, so now we got sine cubed. So we got now sine to an odd power. And we got something modifying the period inside the argument. So I think at this point, it's probably good to put the table up that summarizes how do you find the period in general. Well, if you have any of these cases, sine to an even, cosine to an even, secant or cosecant to an even, or any tangent, even or odd, all the tangents, all the cotangents, you use the formula pi over b. Anything else is the formula 2 pi over b. So that would be sine to an odd, cosine to an odd, secant to an odd, or cosecant to an odd. That would be the formula 2 pi over b. And I put the b in absolute value because if b was ever negative, we don't want to use the negative value for b because our period is a measurement of distance. So that should always be positive. So it's the same formulas you already know. I'm just kind of expanding when you can use them. I'm telling you, you can use them for even more than you knew before. Okay. So any of these 4 trig functions to an odd power, 2 pi over b. Any of the functions up above, pi over b. So let's look at sine to an odd power. What's the formula to find the period when you have sine to an odd power? Yeah?
So 2 pi.
2 pi over b. What's b in this case? Yeah? 2. B is the coefficient of x. So the period of sine cubed 2x is pi. What's the period of cosine? Yeah?
It's the same thing. 2 pi over b.
Yeah, it's really cosine to the first power, which is like an odd, which is 2 pi over b. So in this case, it's 2 pi over 1, which is just 2 pi. So there's your periods of each individual term. What's the LCM?
2 pi.
2 pi. So now every answer that you get is going to have a plus 2 pi on the answer. Let's type it in. So we've got 3 sine cubed 2x. Okay, be a little careful how we type that in. So we've got, we don't want to cube the 3. If you cube the 3, you're going to make it 27 sine 2x. So you need the 3 out in front. And then you need to take sine 2x, close your argument, close the sine function, and then cube it. And now the 3 is not going to be cubed because it's outside. That's 3 sine cubed 2x minus 2 cosine x. Okay, we know the period is 2 pi. So set your window to be 0 to 2 pi. No asymptotes, because sine and cosine don't have asymptotes, so it's all going to be connected. Let's see what it looks like. So remember, you're looking for where it equals 0. How many times does it look like it crosses the x-axis?
At least 6.
Yeah.
We're going to need to zoom into the second and third interval probably. Because it could cross a lot more times.
So it does cross 6 times. Okay, so the most annoying thing about this one is you'd have to do second calc intersect 6 times, find each one. You typically don't have one that's that many. Okay, I already did the intersect, I have one. So it's 0.5. Let's see. 1.25, 1.57. 1.89, 2.65, and 4.71.
We need to label them as x1 through x6.
No, I'm just going to put, I'm going to kind of go like this. Let's move all these over. And I'll just say x is approximately all of those plus, and what would go on the end of each one of them. Yep. 2 pi. That's not really the most mathematically formal way of writing the answer, but that gets the idea of what you're looking for. Okay. Any question how you'd find those 6? just doing one at a time. Yes?
Why was the 2 pi per sine cancel out? And why was it divided by 2 and cancel out?
So the formula is 2 pi over b, and in this case, b is a 2. So it's 2 pi over the 2, and the 2's cancel. All right, so we got the summary of the periods. Anybody need that? All right. So let's look at, so there's a few inequalities. So inequalities. Well, solving an inequality is really the same thing as solving an equation. The difference is when you write your answer, you're not going to just put a plus 2 pi n on a single number. When you write an inequality, your answer is usually a what?
A whole number.
Not necessarily a whole number, yeah? Well, it could be a condown inequality, and what does that look like when you write a solution? It's a what?
Absolute value.
No absolute
You
value.
just said it's in between, like x's between two numbers with like symbols.
And what do you call that when you write something that's describing values between? It's an,
Right.
sometimes you use brackets, sometimes you use parentheses, but that's called an interval. So when you're solving an inequality, instead of just having a number plus 2 pi n, it's an entire interval plus 2 pi n, because that entire interval repeats every cycle. All right, so to solve an inequality, first solve it like you're doing an equation. You're going to find all the zeros. Then, a lot of times it's either going to be between the two numbers that you find as an interval, or it could be from one of those numbers to infinity, if it's an open interval that goes on forever, or negative infinity to one of those numbers. Okay, remember, vertical asymptotes break an interval. So if you're trying to write an interval that needs to pass through an asymptote, you need to break it at the asymptote and then start it again. You cannot pass through a vertical asymptote in a single interval. It needs to break. And the vertical asymptotes are going to be easy to find. I'm not going to give you one that's difficult, right? It would be at like pi or 2 pi. So it's going to be an obvious number. All right, so let's look at this one, where the sine is less than the cotangent.
When you say that, a regular tangent has the weird like lines like this, and they have their vertical asymptotes. So do you mean that like we just set the interval at the beginning of the observable lowest and observable highest like y value for like that? For that like segment?
Well, let's do this one because it'll have an asymptote, and I think it'll probably answer.
Yeah, it's just only two like visual asymptotes. Like remember, is the tangent, and when you have the interval or integral line thing, where it has like the unseen dots that are like imaginary or something.
Yeah. Well, let's do it the same way. What's the sine? What's the period of sine? Yeah, 2 pi. What's the period of cotangent? Yeah, pi. So we're looking at an LCM of what? 2 pi. That's what you're going to need to put on each interval. Okay. So what we're going to do is we're going to solve this problem in one interval and then apply that answer to every interval. So what I would do is put in 0 to 2 pi. You can put sine of x in y1. You can put cotangent in y2. And you're looking for where the sine is under the cotangent, where the blue is under the red. Okay, so let's see where that happens. Okay, well there's the blue. That's just a sine wave. And where is that under the red?
Oh, are we just gonna do the bracket thing, the parenthesis thing of like not including this number?
Yeah, because we do have an asymptote, so we got to be careful with that. So let's make this a little easier to see. So where is the blue graph under the red one? Well, I would say that happens here to here. And then, does it ever happen again?
Yes.
Yeah. There's an asymptote right there. It's exactly in the middle of the screen. If you know what we set the window to, 0 to 2 pi, you should be able to figure out where that green dot is.
Pi.
It's at pi.
Is it also, that's where it's at 0, right?
Yeah,
0.
yeah. The graph of sine also crosses the x-axis right there.
You could do like y at 0 if you wanted. And if you didn't know.
Yep. So these two sections in green are the two answers to the problem, and those two sections are going to repeat every cycle. All right, let's figure out whether we include or not include. Can I include the left end of interval 1?
Yes.
Yeah.
Yes, because that has to do with the window, and the window is 0 to 2 pi. So we can include it. Can I include the right end
No.
of it? No. I can't include it because it's not an equal to. It has to be below. So that's going to be interval 1. How about interval 2? Can I include the left edge of interval 2?
No.
No, because if I try to include the left edge, we've got to think about that asymptote, and it says it has to be below, right? It can't be equal. So I'm trying to think, can we include that? I don't think we can include it because that's an asymptote. So if you include it, how do you know that that's below the red one? You have nothing to compare the red one to because it's at infinite. Well,
When I put it into the graphic table, it says error. When I
Right.
put pi in.
it'll say error for the cotangent.
For the red line.
So I'm trying to think what the right thing to say is. So usually when you say something is below something else, you have a number you can compare here to a number you can compare here. This is going to give you an error. Go on in. If you try to do it.
I have something in your last class.
Oh, sure. Yeah, you can grab it. So I'm going to say we don't include the left end of interval 2. Oh, yeah. Yeah, it's right on the calendar.
Thank you so much.
Oh, you're welcome. Now, how about the right end of interval 2? Can I include that? Can we equal the red line, or do we have to be under it?
It has to be under it.
We have to be under it. Okay, so I think that's how we should set up our brackets and parentheses. What is this number in the first interval? Where does interval 1 start?
0.
Starts at 0. I think, well, actually interval 2. Where does interval 2 start?
Pi.
Starts at pi. Now, to get these other ones, we need the intersects.
X is 9.9045, Y is 0.786 for the
Point.
first interval.
904.
Yep.
Right. So let's say
0.9045.
0.90.
Yep.
And what about the second interval?
Don't have that one yet.
1, 2, 3, 4. Looks like it's a little more than 5. 5.2 maybe.
Um, 5.378.
5.378. So 5.38. Okay. And these two intervals are going to repeat how often? Forever. So I'm just going to put a plus 2 pi n there and a plus 2 pi n there. What that means is you can add 2 pi n to that, and that, and you'll get the same intervals a cycle later. Yes?
I mean, you were saying before that tangent, sine and cosine both all, well, that tangent has a different like cycle than sine and cosine. So therefore, if you have like the tangent and like a cosine like in the same like problem or something, how do you know like what period to use?
Find each period and take the LCM.
Thing. And my other question is for the graph: if it ended if the red line ended above the blue line, if you go back to the graph thing, yeah, if the red line was higher somehow and like it went off the
If it just went off the screen on the right,
like if red somehow ended here and blue somehow ended there, can we say that blue is absolute there?
you'd stop the interval at 2 pi.
But you would have the absolute thing.
No absolute values. No, you just stop your interval at 2 pi.
Well, just because here it's below, and so we have the absolute for 0.
No. So no absolute values, no vertical lines in these problems.
Yeah, that's what I'm talking about. I was like, for 0 you have a bracket.
Bracket, yes.
So if that happened for the end, would there be bracket?
No, it would be a parenthesis. Because if you include the left edge of the window, you don't include the right edge, because think about folding them together like a cylinder. They're the same edge.
Yeah.
So if you include 0, don't include 2 pi. Yeah. Alright, let's look at this. Sine 2x is greater than or equal to x squared minus 1. Now let's just graph it the way it is. Don't move anything left to right. Just put what's on the left in y1. Put what's on the right in y2. And let's do zoom 7. So you're looking for where the wave is above or equal to the parabola. That's what the right side is. It's a parabola. Okay. Is there a section in that graph where the wave is above the parabola? Yeah, definitely, right in the middle of the wave. I would say from like here to here. Now, is that section in green going to repeat every cycle?
No, it's not going to repeat every cycle because there's only that singular instance that the parabola is there and intersecting.
Right, the parabola is not periodic. You're not going to get another parabola over here. You only get one parabola. So the only answer to that problem is exactly what you see on the screen. Don't put plus 2 pi in. So second calc intersect. It's 0.46. Would we include or not include 0.46? Yeah, we can include it because this time it has the equal to. So it'd be 0.46 up to second calc intersect 1.26. Include or not include? Yeah, we can include it again because it says it can equal. So up to 1.26.
Isn't the first one negative?
Was it a negative? Yeah, it was a negative. I missed that. Thank you. Yeah. If I don't put plus 2 pi in, it doesn't repeat. That's the only answer.
For example, 5?
That's example 6.
Oh,
I just put the answer over here because I want to show the graph and I ran out of space.
got it.
Did we write the answer to example 5? I thought I did.
I think you did
yeah,
it
we
on the
did.
last.
Oh, did I do it on a different page? Okay. All right. Okay, so that's the homework for tonight. So 5 to 7, 11 to 15. And actually, this one is odd too. That's not for us. So I'll just go like that. So it's 5 through 7, 11 to 15. And then the rest is all odd. It's 19 to 25 odd, 29 to 31, and 33 to 37. So I think it's 16 plus 17, 16, 17 plus. All right, so we will take a look at that first thing tomorrow.